Imagine you are floating exactly 93 million miles from the only thing keeping you alive. There is no sound. There is no wind. But you can feel it, a warmth that begins at your fingertips, travels up your arms, and settles somewhere deep in your chest like a slow ember catching fire. You look out through your visor and all you see is light. Not the soft amber light of a summer afternoon. Not the warm glow of a lamp in a familiar room. This is something older. Something bigger. Something that has been burning for 4.5 billion years and has no intention of stopping. The surface in front of you churns. It boils. Towers of superheated plasma rise and collapse in slow motion, each one larger than the entire continent of North America. You watch a single loop of fire arc silently into space, a coronal mass ejection, carrying with it more energy than every nuclear weapon ever built, every power plant ever constructed, every calorie of food ever eaten by every human being who has ever lived, multiplied by a number your brain genuinely cannot process. And right now, in this exact moment in history, it is aimed at us. The sun. You think you know it. You have spent your entire life beneath it. You have felt it on your skin, squinted against it through car windows, watched it set in colors that made you stop and stare. It is familiar. It is constant. It is safe. Every single one of those things is a beautiful lie. The sun is not a stable backdrop to your life. It is a nuclear furnace 1.4 million kilometers wide, that is 109 Earths lined up side by side, not stacked, not crammed, but stretched across its diameter like a string of marbles that would take you more than 4 months to drive past at highway speed. Its core temperature is 15 million degrees Celsius. Not 15,000. Not 1,500,000. 15 million. That is a number so large it loses meaning until you realize that a cubic centimeter of solar core, a piece the size of a sugar cube, radiates more energy than 10,000 standard light bulbs running continuously. The sun's surface alone, its relatively cool outer layer called the photosphere, sits at around 5,500 degrees Celsius. For reference, the melting point of tungsten, the toughest metal humanity has ever found, is 3,422 degrees. The sun's surface is nearly twice that hot. And we are talking about the cool part. What most people do not realize, what schoolbooks and screensavers have quietly hidden, is that the sun is not in a steady state. It breathes. It cycles. It builds toward moments of extraordinary violence on an 11-year rhythm, and right now, as you read this, it is approaching one of those peaks. Solar maximum. Scientists confirmed it arrived in late 2024. The buildup has already started. What comes next has destroyed planets before, and Earth has no permanent immunity. The first danger is not dramatic. It does not arrive with a visible wave or a sound. It arrives invisibly, at the speed of light, and by the time you know it is happening, it has already begun killing you from the inside. Solar radiation, specifically the ultraviolet, X-ray, and energetic particle radiation that the sun constantly emits, is held back from Earth's surface by two interlocking shields, the magnetosphere and the atmosphere. Without them, the radiation dose on Earth's surface would reach levels lethal to most complex life within hours. The magnetosphere is generated by Earth's rotating iron core, a dynamo of liquid metal spinning 2,900 kilometers below your feet. It deflects charged particles in a vast invisible shell extending 65,000 kilometers toward the sun. The atmosphere adds another layer, absorbing the highest energy photons before they reach sea level. Now imagine both of those are gone. Or, more accurately, imagine they are temporarily compromised by a coronal mass ejection of extreme power. During the most powerful solar storm ever recorded, the Carrington event of 1859, auroras were seen as far south as the Caribbean. Telegraph operators across North America and Europe received electric shocks from their own equipment. The paper in some telegraph stations caught fire. That event released energy roughly equivalent to 10 billion atomic bombs. It hit Earth when our electrical infrastructure was copper wire and spark gaps. If it hit today, estimates from NASA and the National Academy of Sciences suggest the damage to global power grids, satellite networks, GPS systems, and communication infrastructure could reach between $2 and $20 trillion and take 4 to 10 years to repair. Not 4 to 10 weeks. Years. The grid transformers that power modern civilization, each one weighing up to 400 tons and taking 12 to 18 months to manufacture, cannot be quickly replaced. The world you currently inhabit runs on a power infrastructure that a single extraordinary solar event could collapse inside of 90 seconds. The radiation danger deepens when you consider what happens in space, away from Earth's protection entirely. NASA's Parker Solar Probe, the closest humanity has ever sent a spacecraft to the Sun, launched in 2018 and has skimmed within 6.1 million kilometers of the solar surface. At that distance, it experiences radiation levels that would deliver a lethal dose to an unshielded human in under 2 minutes. The spacecraft is protected by a 11.4 cm carbon composite heat shield that must endure temperatures of 1,377 degrees Celsius on its sun-facing side while keeping instruments at room temperature on the other. Engineers describe this as one of the most difficult thermal engineering problems ever solved, and the probe carries no crew because no shield thick enough to protect a human body could also be light enough to launch. Radiation is not just a problem of temperature or burns. At high energies, it is a problem of ionization, charged particles tearing through your DNA like a bullet through paper, not destroying cells outright but corrupting their instructions, turning them into engines of cancer, confusion, and organ failure. Astronauts on the International Space Station receive a radiation dose roughly equivalent to 150 chest X-rays every 6 months, despite being within Earth's partial magnetic protection. Outside that protection, on a journey toward the Sun, the dose rate increases dramatically with every million kilometers you travel inward. By the time you arrived at a distance equal to Mercury's orbit, still 57 million kilometers from the surface, your cumulative radiation dose would exceed safe lifetime limits within days. The second layer of danger is temperature, and it behaves in ways your intuition will reject. Space near the Sun is not uniformly hot. In fact, the vacuum of space itself holds almost no heat in the conventional sense because heat requires matter to transfer through, and space is nearly empty. What kills you near the Sun is not the temperature of space but the direct radiation load, the photons and charged particles striking your body and your spacecraft continuously, without the buffer of atmosphere or distance. At Earth's distance, solar irradiance, the energy received per square meter, is approximately 1,361 watts. That is about the power output of a standard hair dryer, concentrated on every square meter of your body, continuously. Move to Mercury's distance and that figure quadruples. Move to the distance where Parker Solar Probe operates and it increases by a factor of nearly 500. That means every square meter of your suit would receive the equivalent of nearly 700,000 watts. For comparison, a typical welding arc produces about 10,000 watts. Your suit would not slowly warm. It would not gradually fail. It would vaporize. The materials do not exist to withstand that exposure for any meaningful duration with a human body inside them, and the impossibility here is not one of budget or ambition, it is thermodynamics refusing to negotiate. The Sun's atmosphere, the corona, introduces a third danger that has puzzled scientists for over a century. By every law of thermodynamics that governs your everyday experience, the layer further from a heat source should be cooler than the layer closer to it. The Sun's surface sits at 5,500 degrees Celsius. But the corona, the diffuse outer atmosphere that extends millions of kilometers into space, reaches temperatures between 1 and 3 million degrees Celsius. 1 million degrees. That is roughly 200 times hotter than the surface directly below it, and after decades of study and the direct observations made possible by Parker's Solar Probe, scientists now believe the heating is caused by nanoflares, tiny, continuous magnetic reconnection events, and by plasma waves carrying energy outward from below. What this means practically is that any object entering the corona does not encounter a gradual warmth. It encounters a superheated plasma bath at temperatures that are, without any scientific exaggeration, impossible to shield against with any material currently known to science. The corona would not melt a spacecraft. It would disassemble it at the atomic level. A fourth danger hides inside the sun's apparent calm, solar energetic particle events, or SEP events. These occur when a solar flare or coronal mass ejection accelerates protons and electrons to velocities approaching a significant fraction of the speed of light. During a major SEP event, these particles arrive at Earth orbit within minutes to hours of a solar eruption, too fast to evacuate astronauts to shelter before exposure begins. In August 1972, between the Apollo 16 and Apollo 17 missions, one of the largest SEP events in recorded history struck Earth's inner solar system. Had Apollo 17's crew been in deep space rather than safely back on Earth, estimates suggest the radiation dose they would have received could have been fatal or severely incapacitating. They survived only because the timing was narrow by weeks. NASA has never found a reliable, lightweight solution to this problem. The shielding required to block SEP protons at extreme energies would need to be so thick and massive that launching the spacecraft would be, by current rocket technology, impossible. The fifth danger is the one you likely never expected. It is the silence. Not metaphorical silence, literal electromagnetic silence caused by solar radio burst interference. When the sun erupts, it does not just release particles and radiation. It releases enormous bursts of radio frequency energy across a wide spectrum, overwhelming communication systems both on Earth and in space. During the largest solar radio bursts, GPS signals degrade or fail entirely. Aviation communication systems experience blackouts. Navigation becomes impossible for surface vessels and aircraft. This is not a science fiction scenario. It happened in September 2017 when a series of X-class solar flares caused GPS errors and radio blackouts across the dayside of Earth for hours. For an astronaut near the Sun, the communication disruption would be total. Not reduced. Not delayed. Gone. You would exist in genuine isolation from all of humanity, in a vessel being bombarded by radiation and heat, with no ability to send or receive information. Your distress signal would dissolve into the noise of the star trying to kill you. Now consider what all of this does to the human body, not in theory, but in the measured, documented, irreversible ways that NASA has catalogued through decades of study on astronauts aboard the International Space Station, operating at a polite distance of 408 kilometers above Earth, well within the magnetosphere's protection. In that relatively safe environment, astronauts lose between 1 and 2% of bone density per month. Over 6 months, a standard ISS rotation, that is a loss equivalent to what a person might experience over a decade of natural aging. The bones do not simply become fragile. They become fundamentally altered, and studies have shown that even after years of recovery and rehabilitation on Earth, some astronauts never fully return to their pre-flight bone density. Now extend that exposure time and increase the radiation load by a factor of hundreds. Muscle atrophy follows a similar trajectory. In microgravity, without the constant load-bearing demands of living in Earth's gravity, the body begins deconstructing its own muscle tissue with quiet efficiency. The heart, which in a lifetime of fighting gravity has evolved into a powerful, roughly spherical pump, begins to change shape in microgravity, becoming more spherical as its workload decreases, reducing its efficiency by a measurable percentage that researchers are still working to fully quantify. Vision impairment is one of the most alarming discoveries of long-duration spaceflight research. Over 60% of astronauts on long missions have reported changes in vision, and scans have revealed structural changes in the eye itself. The optic nerve swells, the shape of the eyeball flattens slightly, and the area of the retina responsible for sharp central vision shows signs of pressure-induced damage. The cause is believed to be a shift in cerebrospinal fluid distribution in the absence of gravity, creating elevated pressure inside the skull. It is called spaceflight-associated neuroocular syndrome, and there is currently no reliable treatment or prevention method. The immune system, meanwhile, destabilizes. Dormant viruses in the human body, including herpes simplex, varicella zoster, and Epstein-Barr, reactivate in over half of astronauts during and after flight. The body's natural suppression mechanisms weaken. Inflammation increases. Wound healing slows. By the time you arrived at even the midpoint of a journey toward the sun, if such a journey were somehow survivable in terms of heat and radiation, you would already be experiencing cascading physiological collapse with no medical team, no hospital, and no treatment facility within any practical reach. The psychological dimension is its own catastrophe. Studies from the Mars 500 isolation experiment, which confined 6 volunteers in a simulated spacecraft in Moscow for 520 days, documented monotony-induced inactivity, sleep disruption, psychological disengagement, and interpersonal conflict that intensified over time rather than stabilizing. Antarctic winter-over crews and submarine crews on extended deployments show similar patterns of cognitive deterioration, emotional blunting, and in some cases, severe psychological breaks. On a real solar approach mission, the awareness that you cannot leave, that there is no abort procedure, no emergency landing, no turning back, would compound every psychological stressor with a weight that ground-based isolation studies cannot fully replicate. You would not return to Earth as the same person. The science is unambiguous on that point. The journey itself is its own category of impossibility. The closest the Sun gets to Earth is approximately 147 million kilometers, during perihelion in early January. With the fastest spacecraft humanity has ever built, the Parker Solar Probe, which at its closest approach reaches speeds of approximately 692,000 kilometers per hour, a direct journey from Earth toward the Sun would take roughly 90 hours to close that distance under ideal conditions. But Parker is not carrying fuel for the full trip. It uses gravity assists from Venus to adjust its trajectory, a process that takes years and multiple orbital passes to achieve the close approaches it makes. A crewed mission could not use the same approach. The rocket equation, the fundamental mathematical relationship between fuel mass, spacecraft mass, and velocity, makes a crewed solar approach mission not just difficult but physically impossible within any near-term understanding of propulsion. The amount of fuel required to decelerate a crewed vessel at the inner solar system, protect it from radiation, supply it with life support for months, and then somehow return it to Earth would require a spacecraft so massive that no existing or near-future launch system could lift it off Earth, let alone accelerate it to useful speeds. For every kilogram of payload you want to move and return, you need many more kilograms of fuel. And fuel requires more fuel to accelerate the fuel. The numbers collapse into themselves. It is not a problem that a bigger rocket solves. It is a problem that the physics of chemistry combustion cannot solve at all. You might imagine that ion drives or nuclear propulsion could change this calculus, and they represent genuine hope for long-duration deep space travel, but they introduce their own constraints of thrust, time, and shielding mass that do not resolve the fundamental impossibility of protecting human biology in the Sun's proximity. Communication delay to the inner solar system is measured in minutes rather than the tens of minutes to hours experienced in deep space, which might seem like a comfort until you realize it means nothing for the radiation environment, the thermal load, or the mechanical dangers. Even a few minutes of communication delay is enough to make real-time rescue coordination meaningless. There is no return window. There is no rescue mission. There is no way back. Let the full weight of this settle. The Sun, the object that rises every morning in your sky, that you have never given a second thought while going about your day, is a 4.5 billion-year-old nuclear reactor emitting radiation that kills unprotected biology in minutes, plasma temperatures that melt every known material, particle bursts that can collapse global power infrastructure in seconds, and a corona of million-degree superheated gas that disassembles matter at the atomic level. This is not primarily an engineering problem. It is a physics problem. The laws of thermodynamics, the rocket equation, the biology of the human body, these are not obstacles to be overcome with larger budgets or bolder engineers. They are boundaries written into the nature of reality. What robotic missions can do, what Parker Solar Probe has done, what ESA's Solar Orbiter continues to do, is extraordinary. They can get closer than any human ever could, collect data that transforms our understanding of stellar physics, and give us warning systems that might one day protect civilization from the worst of what the Sun can deliver. Future technology, particularly in the areas of radiation shielding, compact nuclear propulsion, and possibly even directed energy systems, may eventually push the boundaries of what is survivable further inward. But honest scientific assessment places a crude solar approach mission not within decades but potentially within centuries, and only under conditions of technological advancement we cannot yet predict. Step back now. Let the sun recede to its proper distance. Look at where you are standing, on a planet wrapped in a magnetic field generated by its own molten core, blanketed in an atmosphere that filters lethal radiation to harmless levels, kept at temperatures where liquid water exists on the surface, orbiting at a distance precise enough that neither the oceans boil nor freeze on any permanent timescale. The terror of the sun, its radiation, its heat, its indifference to biology, makes Earth's existence feel less like an accident and more like something improbable enough to be called precious. We are creatures of this thin, protected shell. We evolved for exactly this distance, this temperature, this radiation level. Every feature of our biology, our eyes tuned to the sun's peak visible wavelengths, our bones built for this exact gravity, our immune systems calibrated to this exact environment, is the product of 4 billion years of life learning to live precisely here, and nowhere else. The universe is not designed for us. But this planet is, in every way that matters. That is not a limitation. That is a miracle. If this gave you something to think about, take a moment to subscribe. There is so much more out there, waiting to change how you see the sky.